Hello everyone, we are the students studying in the Department of Physics in National Chongqing University. Here's the condensed matter physics class. For this class, here's our final project. The topic we are going to talk about today is the superconductivity. The membership of our group is composed by three persons, Qing Yao, Kaijun Cai, and Ting Yu Xu. The advisor is Wenming Huang Professor. Here's our outline. We will divide our project into two parts, the history plus experiment part and the theory part. For theorism, we will talk about the BCS theorism and the Josephson effect. Here's our opening. My name is Kaijun Cai, and the student ID list is below. And I'm going to talk about today is introducing the history and the experiment finding of superconductivity. What is superconductivity? Superconductivity is a phenomenon where certain material exhibit the zero electrical resistance. This is very important. And the expulsion of magnetic field when cool below a characteristic critical temperature. Critical temperature later we will call it Tc. It is a macroscopic quantum manifestation. It serves as a primary example of how collective interactions in a many-body system lead to a behavior that cannot be predicted by looking at the individual particle alone. So you can see four special phenomena for superconductivity. The first one is emergence and many-body physics. The second one is the spontaneous symmetry breaking. The third one is the macroscopic quantum phenomena, and the last one is the paradigm of phase transition. The graph we are showing here below is the superconductor LK99. It will be pronounced and produced in or by South Korea in 2023. It will give us a new finding introduction. Okay, back to the history of superconductivity. Before new findings and phenomena, here's the three main thoughts about the behavior of electrical resistance near 0 Kelvin at temperature close to 0 Kelvin. The first one is the electron freezing hypothesis. Lord Kelvin suggests that as temperature decreases, electrons would eventually freeze onto their parent atom, leading to a loss of mobile charge carrier. Thus, resistance will increase to infinity as temperature close to zero. The second is the residual resistance. Matheson predicts that the resistance will decrease with temperature, but level off at a constant value due to the impurity in the crystal lattice. The third one is Stewart's perfect conductivity viewpoint. He proposed that in a perfectly pure metal, the resistance will decrease linearly and reach exactly zero at 0 Kelvin. As the time goes by, some experiments success and some phenomena can be proved. The first experiment is Ohm's discovery of zero resistance in 1911. Joachim Hermelin Owens settled his debate after successfully liquefying helium by measuring the resistance of pure mercury at a very low temperature. At this low temperature, you will find instead of a gradual decrease or a sudden increase, the resistance dropped abruptly to unmeasurable level at 4 Kelvin. Just like you can see on the right hand side of the graph we show, there was an inclined line There are three dots when the temperature goes from the right hand side around 4.4 Kelvin. It will be around, the resistance will be around 10 to 15 ohms. But when the temperature close to 4.2 kelvins, the resistance will abruptly drop to around zero, but not zero. It's approaching or nearly 5 or 10 of 5 minus 5 ohms. That proves that this was not the gradual perfect conductivity, like duals expect, but a phase transition to a completely new state of matter. The second experiment is, or the second experiment finding is the Meissner effect. In this hypothetical perfect conductivity proposed by Lenz's law, he says it will freeze the magnetic field inside, but the Meissner effect proves that inside the superconductor, all the magnetic field, or in vector or in real number, will equal to zero. That means demonstrating the perfect diamagnetism. He also discovered that the superconductors are more than just perfect conductor. When the material is placed in a weak magnetic field and cooled through its Tc, Tc here means the critical temperature, the magnetic flux line that previously penetrated the material are actually expelled, just like a graph we show on below. In origin, the magnetic line will straightly downward, but on the right hand side, it will expel outside and around this sphere. The third experiment is the head capacity analysis. In normal metal, the electric heat capacity is proportional to the temperature. We can list it into equation CEL equals to gamma T. C here means the capacity, gamma means kBT. In 1932, Kinson and Koch scientists observed a sharp jump in heat capacity at critical temperature, indicating that a second-order phase transition. And in 1954, Korach and his colleagues measured the heat capacity at even lower temperatures and found it will decay exponentially, so that we can see the equation. The capacity will proportional to the exponential of minus delta over kBT. Delta here means the energy gap. That means we prove the existence of an energy gap between the ground state and the excited state. Here are the figure we take example for the head capacity experiment. We take gallium as an example. We compare the normal and the superconductive side of gallium. For the normal side, like a white dot, it will equal or on the line horizontally. But for the dot in black one, you can see it will slowly grow up to the 1.5 for the y-axis. Y-axis here means the C over T. But for the temperature close to 1.2, or the C over T equals 1.4, it will abruptly drop to the normal state. And the right hand side, that proves that the C over gamma T is proportional to the exponential minus 1 over T. That means proportional to the temperature, exponential 1 over temperature. The fourth experiment is the isotopic effect. For melting a little sunrising, Emil Maxwell and Lestime Reynolds independently discovered that the critical temperature depends on the isotopic mass of the atom in the lattice. The relationship follows the power law. M alpha times Tc equals constant for most simple metal. Experimental value of alpha for different metal shown in list. For example, for a Zn, the alpha will equal to 0.45. This finding making a little summarizing for me. The quantitative prediction of elementary microscopic theorism, so that we can see for the critical temperature, energy gap, and specific heat, it will follow the rule, just as I said. And the right hand side in this graph, it also shows that at the critical temperature, the head capacity will drop like the normal in blue one. The red one is the superconducting side.
Hello everyone, my name is Ting Yushi, and today I will be introducing the basic theory of superconductivity, specifically focusing on the thermodynamics of the superconducting transition. Let's begin by looking at the fundamental nature of this transition. First, the transition between the normal state and the superconducting state is thermodynamically reversible. This is a crucial point because it allows us to apply the law of the equilibrium thermodynamics, much like we do when study the phase transition between a liquid and a gas. Second, we must consider the Meissner effect. In a type 1 superconductor, the internal magnetic flux density is a zero. This tells us that the superconductor is the perfect diamagnet to actually state of zero internal field. The materials generates the surface current that creates a magnetization that perfectly cancel out of the applied field. Mathematically, as shown on the slide, we express this as here. This perfect diamagnetism is the cost. The material paid to remain in the superconducting state. Now let's examine energy involved using the thermodynamics identity. The change in free energy per unit volume, dF, during this transition in related to the work done to include the magnetic field here. By substituting our earlier expression for magnetization into this integral, we find that the applied magnetic field increase. The free energy density of the superconducting state also increase. Specifically, the energy rises quadratically with the field, as you can see from the equation here. This represents the magnetic energy cost required to push the magnetic field out of the superconductor volume. This brings us to the concept of the condensation energy. This condensation energy is the saving in energy less the electron gain by Fraunhofer pair. We define this as the difference between the free energy of the normal state and the superconducting state at zero field. In the graph on the here, you can see two lines states is a normal state and the superconducting state. The normal state is almost independent of the magnetic field. However, the superconducting states start lower but rise quadratically as the field increases. The point where these two lines intersect in the equilibrium point. At this specific field, known as the critical magnetic field, the two phases are in equilibrium. If the field increases any further, the energy cost of excluding the field becomes too high, and the material reverts to its normal state. So for example, in element at the absolute zero, the critical field is 105. This gives us the calculus condensation of energy of approximately 439, which matches experimental calorimetry data almost perfectly. So the superconducting state is stable only as long as the energy saved by electron pairs exceeds energy cost of including the external magnetic field. This balance defines the boundary of the superconductivity. In our previous discussion, we looked at the thermodynamics of the superconductivity. Now we will shift our focus on the electron dynamics that govern this material, especially in London equation. In normal metal, electrical conduction follow Ohm's law, where current density is proportional to the electric field. However, Ohm's law fails to explain the most famous property of the superconductivity, the Meissner effect. So to solve this, the London brothers proposed a new basis assumption in a superconducting state. The current density is direct proportional to the magnetic vector potential here. The equation is expressed as this. So this leads us to a critical parameter called the London penetration depth. This value represents the depth to which a magnetic field can actually penetrate into the surface of a superconductor. Looking at the microscopic formula, we see it depends on the density of the superconducting electron, N, and the layer mass here. It's important to note that the foam thin film, where the thickness is much smaller than penetration depth, the magnetic field can pass through almost uniformly, means the Meissner effects remain incomplete in very thin sample. Now let's see how the London equation actually explains the Meissner effect during the derivation of the magnetic field penetration equation. By combining the London equation with Maxwell equation, specifically here this one, we obtain a special distribution equation for the magnetic field inside the superconductor. This differential equation describes an exponential decay profile. If we look at the semi-infinity superconductor model shown in the diagram, assume the magnetic field in parallel to the boundary. The field distribution is given by this one. While this tells us that the magnetic field does not vanish abruptly at the interface. Instead, its decay exponential as it moves into the material deep inside a bulk superconductor, where the distance s is much greater than the penetration depth. The field approaches zero. This provides a perfect mathematical explanation for why the interior of a bulk superconductor is shielded from magnetic field. So, while the London penetration depth tells us how magnetic field behave, we also need to understand how the superconducting electrons themselves behave over distance. That brings us to the coherent length. Physical, the coherent length describes the minimal distance of which a superconducting electron density can undergo a significant spatial variance. You can think of it as the size of a range of a Cooper pair. This is a intrinsic coherent length, which relates to material energy gap and the Fermi velocity. It's a one nothing that the coherent length is highly dependent on the purity of the material. In impure or alloyed material, the actual coherent length becomes shorter than intrinsic value. If you look at the table of the slide, you can see how these two lengths scale. Now we discussing one of the most significant breakthroughs in 20th century physics, the BCF theory of superconductivity, named after John Bardeen, Leon Cooper, and Robert Schrieffer. Cooper pair, let's look at the core mechanism. At the heart of this theory are Cooper pair. In a normal metal, electrons repel each other because they are both negatively charged. However, BCF theory shows that at low temperature, electrons can overcome this repulsion to form pair. These pairs consist of two electrons with opposite momentum and opposite spin, denoted as K up and minus K down. This specific configuration is known as wave pairing because these pairs act more like boson than fermion. They can condense into a single quantum state, allow them to follow through a lattice without scattering. You might wonder, how can two negative charge particles actually attract each other? The answer is lies in electron lattice interaction. As an electron moves toward the critical lattice, it exerts an attractive force on the surrounding positive ion, causing a slight ripple or deformation in the lattice. This creates a region of increased positive charge density. A second electron is then attracted to this positive region. Effectively, the lattice acts as a mediator, creates an attractive force between the electrons. This pairing lowers the system overall energy, make the superconducting state more stable than the normal state. Moving on to the achievements of the theory, BCF theory successfully predicts several key phenomena. In the energy gap, it's proof there in an energy gap between the ground state and the excited state. This gap is why superconductors don't lose energy to small thermal fluctuation. Meissner effect. The theory naturally explains why superconductors expose magnetic field, phenomena known as Meissner effect. Now, flux quantitation. It's confirmed that magnetic flux in a superconducting ring is quantized in units of 2 electrons. Proof that the charge carrier are indeed electron pair are not single electron. Final, one of the most powerful aspects of the theory is to predict the transition temperature using this formula. Here, theta represents the Debye temperature, and U is the strength of the abstract interaction, and D is the density of state as the Fermi energy. This equation shows that Tc is intimately tied to vibration of the lattice and the electronic structure of the material. In conclusion, BCF theory remains the foundation of our understanding of conventional superconductors and continues to be a cornerstone of condensed matter physics. Now move on our next presenter, Qin Yao.
The next presenter is me. My name is Junyin Yang. Today I will introduce the Josephson effect, starting from a single junction and extending to quantum interference in superconducting loops. Let me first describe the basic physical setup of a Josephson junction. Two superconductors separated by a thin insulator. Let phi 1 and phi 2 be the probability amplitudes of Cooper pair on the two sides of the junction. To describe the quantum coupling, the time evolution of these amplitudes is given by the time-dependent Schrödinger equation. The parameter T represents the tunneling coupling between the two superconductors and has a dimension of a frequency. If the insulating barrier is very thick, the coupling vanishes and no Cooper pair tunneling occurs. To understand the dynamics, we rewrite the wave function in a more physical form. Each probability amplitude is written in terms of particle number and a phase. With this decomposition, plugging these equations into a time-dependent Schrödinger equations gives the following relations. These equations show that tunneling is governed by the coupling between particle number and the phase. So the phase difference becomes a key variable. Now we look at the consequence of these equations in zero voltage case. Separating the real and the imaginary part of two equations gives the particle number dynamics. It is clear that the rate of charge of N1 is equal to the negative of the rate of the charge of N2. The conservation of particle number is therefore satisfied. The phase dynamic of two superconductors is given by the following equations. For two identical superconductors, with N1 is approximately equal to N2, the phase difference remains constant in time. The supercurrent across the junction is proportional to the rate of Cooper pair transfer between the two sides. As a direct consequence, this leads to the DC-Josephson current phase relation. A finite current supercurrent can flow across the junction even in the absence of any applied voltage. Next, we consider what happens when a voltage is applied across the junction. When a DC voltage V is applied across Josephson junction, the junction remains insulated but allows Cooper pair tunneling. A Cooper pair experiences a potential energy difference QV across the junction, where the charge of a pair is negative 2e. The equations of motion are therefore modified to include the potential energy terms. One equation picks up a negative EV term, while the other picks up a positive term. These equations replace the little voltage case and form the starting point of the AC Josephson effect. We first examine how the applied voltage affects the particle number dynamics. The real part of the voltage modified equations determine the particle number dynamics. The rate of charge of the particle number, on each side of the junction depends on the sign of the phase difference. Interestingly, the results remain the same. These two equations shows that Cooper pairs are conserved and are transferred coherently between the two superconductors. The particle number dynamics is identical to that of the DC-Josephson effect. We now turn to the phase dynamics. Under applied voltage, an applied DC voltage introduces an additional term proportional to EV over H bar in the phase equations. For two identical superconductors with N1 is approximately equal to N2, the voltage terms dominate the evolution of the phase difference. The applied voltage therefore drives a time-dependent relative phase between the two superconductors. As a result, the supercurrent becomes time-dependent. For identical superconductors, the phase difference evolves linearly in time under constant voltage. Thus, the current phase relation gives the Josephson current. This directly leads to an oscillating current. The supercurrent therefore oscillates in time, even though the applied voltage is constant. The oscillating frequency is given by omega equals 2 EV over H bar, which defines the AC Josephson effect. Now we extend the discussion to a superconducting loop with two junctions. The phase difference is determined by the total magnetic flux. The total magnetic flux comes from both external magnetic field and currents circulating in the loop. Particularly in the absence of magnetic field, the phase difference is restricted to 2 pi s, where s is an integer. Applying a magnetic flux through the loop introduces a relative phase shift between the two junctions. The total current is determined by the interference between the two junctions. The phase difference across the two junctions are shifted by the applied magnetic flux. One phase picks up positive E phi over H bar C, while the other picks up a negative shift. As a result of interference, the supercurrent through each junction follow the Josephson current phase relation. The total supercurrent is sum of the current through the two junctions, so it oscillates periodically with magnetic flux due to quantum interference. In addition to interference, finite junction size introduce diffraction effect. This figure shows the periodic current, and the show periodic variation is due to interference between the two Josephson junctions, as predicted by E phi over H bar C equals S pi, where S is an integer. The long periodic variation is diffraction effect that arises from finite dimension of each junction. So the measured current is determined by both loop interference and the geometry of the junction. Finally, we combine interference and diffraction to understand the measured current. A single Josephson junction has a rectangular cross-section with a finite width W and thickness T. Since the phase difference depends on the transverse position X, by integrating over the entire junction width, the total supercurrent can be obtained. For a single junction, the magnetic field acts over an effective area Wt, producing a diffraction envelope, and the supercurrent follows a diffraction-like current field relation. This combined effective explains the coexistence of short-period oscillations and the long-period envelope in the experimental data. In conclusion, Josephson junction provide a direct and elegant realization of macroscopic quantum mechanics, link phase coherence, electromagnetic fields, and measurable supercurrents. This concludes my presentation. The final slide shows the reference for this presentation. Thank you for your attention.